Hi there everyone. Who makes the best 5-inch motor? In this video, we're going to be looking at motors from FPVCycle, RCinPower and iFlight and comparing their key features, their performance, their thrust, their responsiveness, and also the size, weight and efficiency of the motor to try and find out which 5-inch motor is going to be right for the type of quad that you like to build. There's no time to waste, let's get right into it. So let's start by looking at the motors that we're going to be testing today. Of course, no 5-inch motor shootout would be complete without the FPVCycle 25mm, and I've got the lower kV version here, the 1870 kV for 6S. I've got my benchmark motor, the Emax ECOII 2207, 1700 kV, and then I've got a few motors from iFlight. We've got the Xing 2207 in 1855 and 1950 kV, and the Xing 2506, which is the closest size to the FPVCycle 25mm at 1850 kV. So very similar kV, very similar size. We've also got the Xing 2208. Now this is my preferred motor for 5.5-inch props. And it's actually a very similar volume to the 2506, maybe ever so slightly bigger, but very, very similar volume. We've also got some motors from RCinPower, the GTSV3 2107 with 1980 kV, so a really high kV 2107 motor, and then a more moderate 2306, so smaller volume at 1880 kV, and the WASP major with a kind of strange size. It's 22.6 by 6.5 millimeters, and I have 2 kVs of that, the 1860 kV and the 2020 kV. So as you'll see, this is kind of a pretty wide range of typical 5-inch freestyle motors. And also we have a nice range of kV as well. So we can really see the effect of different motor shapes, different motor sizes, and different motor kVs in this 5-inch category. When we're looking to pick the best motor for any quad, not just 5-inch freestyle, we want to look at the key features and durability of the motor. We also want to know the thrust, the efficiency, the power and the responsiveness of the motor, because that's going to be really important to how the quad flies and feels in the air. We also want to consider the size and the weight of the motor, because not only is the motor a significant portion of the quad's weight, but because it's so far out on the ends of the arms, it has a really big effect on the moment of inertia of the quad on all 3 axes. So it's really important to get that size and weight balance right. All of the performance numbers that you're going to see in this video were taken using a 5 by 4.5 by 3 V1S prop made by HQ. Now this is a relatively steep 5-inch freestyle prop, and so it should be putting the motors under a very representative amount of load. The first feature that I want to talk about is Unibell motors versus motors that have 2-piece bells. Now, the vast majority of the motors we're going to be looking at today are Unibell designs. And what that means is that the bell, that's typically machined out of aluminium, extends all the way down over the flux ring and the magnets. This provides a lot of area to friction fit the flux ring into the bell, and basically makes it impossible for the flux ring ever to fall out of the bell, even in a very, very hard crash. In a 2-piece bell, which is used in the ECOIIs and in the FPVCycle Imperials, rather than the flux ring being fitted into the bell, the flux ring is friction fit onto these tines that come down from the bell and separate the magnets of the motor. Now, these tines obviously have a very small area compared to the whole area of the bell, and therefore the friction fit of the flux ring is not so secure, and in a hard crash the flux ring can actually slide down the tines, and this often results in the tines being bent, the magnets potentially coming loose, and can often result in basically the destruction of the motor. So I know that FPVCycle are working on Unibell designs for their motors, but as of right now I would always suggest prioritizing a Unibell design motor, because it's just not going to have this problem of dropped bells in heavy crashes. And that really does contribute to the durability of the motor. Another feature that I think contributes to the durability of a motor is a shock-absorbing O-ring. Now, iFlight include a small O-ring between the bell and the top bearing on their Xing and their Xing 2 motors, and you can see here I've tried to bring it out in green in this schematic. This O-ring is designed to reduce the vertical shock to the top bearing in a hard crash. And bearings are most delicate in the axial direction, so the easiest way to damage a bearing is with an axial impact. Having this small O-ring here will just cushion that blow a little bit and hopefully prolong the life of the bearing. I think it's a nice to have feature. It's certainly not essential, but it's something that is good to see, an attempt to protect that bearing against that type of impact. That brings us on to thrust and efficiency. And I've plotted all 10 of the motors that I've tested on a graph of thrust on the x-axis versus electrical power consumed on the y-axis, so you can compare how much thrust each motor produces and how much power it requires to do that. If we look at peak thrust first, we can see that the 25 size motors, the 2506 and the 25mm motor, put up the biggest thrust numbers. And that's to be expected. The larger the motor is, the more torque it's going to have and the more thrust it's going to be able to produce on any given prop. However, it's also worth noting that the WASP motor with 2020 kV, so a slightly higher kV 22.6 by 6.5mm motor, also put up almost exactly the same thrust as the FPVCycle 25mm, although it did consume just a little bit more power to do it. And we also see that even a 2107 sized motor could put up more than 1600 grams of thrust, provided that the kV was high enough. So when we're looking at these larger size motors, we do also have to consider motors that are smaller but have a higher kV, because they can draw a similar amount of power and produce a similar amount of thrust. The important thing to be aware of here is that smaller motors that are drawing as much power as bigger motors are going to get hotter, and so that's something to be mindful of. And if you do find that a high kV motor is getting too hot, but you still want to have the same power, then you can move to a bigger size, and it should be a motor that stays cooler. If we look at efficiency, we can see that again the ECOII 2207 does well in terms of efficiency, as does the 2208. In fact, it was the most efficient motor in my testing. It didn't produce the most thrust, but it did it very, very efficiently. The RCinPower WASP motor with the lower kV, 1860 kV, was more efficient. And if you compare the 1860 kV to the 2020 kV, you can see that lower kV motors in general are more efficient than higher kV motors with the same dimensions. A real standout for efficiency was actually the RCinPower Smoox 2306 as well. This proved to be a really, really efficient motor, particularly considering it's a slightly smaller size, 2306, and a moderate kV, 1880 kV, rather than 2000 kV. So that did very well in terms of efficiency. If we look at weight, the 25 size motors, the 2506 and the 25mm, were up around 40 grams. So they're pretty heavy for a 5-inch motor. If we look at some more traditional sized 5-inch motors, we see that they tend to come in around 34 grams, 33, 34 grams. The ECOII, a little bit heavier at 36 grams. So obviously, in trying to make a motor that's very low cost, it has added a little bit of weight. The smaller motors, and particularly the RCinPower motors, are quite impressive in terms of weight. They're coming in at under 33 grams, most of them. And that's really impressive. The Xing 2 also very respectable at 33.7 grams. The exact weight that you get when you weigh these motors is going to depend on the length of wire that they have. All of these motors were measured with the same length of wire. If you're shopping for motors, you're going to be exposed to a lot of marketing BS that you need to be inoculated against. And if you've been in the hobby for a while, you probably already know what I'm about to tell you. a lot of motors are marketed as having improved low throttle control, improved low throttle management, better low throttle resolution, and all of this is just BS. All motors I've tested have almost exactly the same shape, thrust versus throttle curve. No motor can claim to have improved low throttle control over any other, just simply doesn't happen that way. Motors that make less thrust overall, because they're smaller or they have a lower kV, are going to have more resolution across the whole throttle range, because the same movement of your stick, of your throttle stick, is covering a smaller range of thrust. A big, powerful motor, particularly something like a 25mm size motor, it has a lot of top end thrust, and therefore it's also going to have less resolution at the low end. The same movement of your throttle stick is covering a wider range of thrust, so you have less resolution. In general, a more responsive motor is going to be able to hold the quad more stable and deliver a smoother flying quad. And also a lighter weight motor, which has less moment of inertia that it's contributing to the quad, is also going to allow the quad to fly a little bit smoother. So looking for motors with good responsiveness and good power to weight ratio is also important. If we look at the responsiveness of the motors now, I think it tells a really interesting story. As we would expect, taller and narrower motors accelerate faster than shorter and wider motors. So we see really great performances from the 2107, the 2207 and the 2208 size. However, the bigger motors, the 25mm size motors that have more torque because they are bigger, do not accelerate any faster with this prop than the 2207. And so clearly, although they do generate more torque, they also have greater inertia, and that's definitely counteracting the greater torque that they can produce. The other interesting result is that the Xing 2 motors with their center slotted magnets are very, very fast to accelerate, among the fastest on test. But they are slightly slower to decelerate. And so there may be something about those center slotted magnets that while they're reducing the amount of torque ripple that the motor is experiencing, they may also be affecting braking performance just slightly. That said, I think that the improvement in acceleration is probably worthwhile having, even if you do see this small penalty to the deceleration of the motor. And this brings us nicely to the key question that I want to tackle in this video. When should you choose a bigger motor, i.e. one with a larger stator volume? And when should you pick a motor with a higher kV, assuming that what you're looking for is more performance, more top-end thrust and power? And we can see the trade-off here by looking at torque versus RPM and amp draw versus RPM. So if we look at torque versus RPM, for a standard 2207 motor, the torque curve is going to look like a straight line that's just linearly decreasing. And what this means is that as the motor spins faster, it's capable of producing less torque. And the reason for that is that the back EMF builds up as the RPM increases. That limits the maximum current that can flow through the motor and therefore its maximum torque. We also have these grey lines on this chart. Now these represent different props, and this is showing the relationship between the RPM of the prop and its torque requirement. So if this is our full throttle torque versus RPM curve for a motor, we can see that for this 2207 motor, it's going to be able to generate this much RPM with a 50-30, but less with a 50-45, less with a 50-51, and less with a 60-40. And it's where this torque RPM curve intersects with the prop curve that's going to be the full throttle performance of the motor. Now let's look at a 2506 motor. Now this is a larger motor with more stator volume, but it has the same kV as our 2207. And because it has the same kV, that means that its no load RPM, i.e. the RPM where it generates zero torque, is going to be the same as the 2207. So the lines meet down here. But because it's a bigger motor, it's going to be able to generate more torque than a smaller motor at all RPMs. So we can see that the line starts off higher and decreases more steeply. We can also see that this larger motor, the 25mm size motor, will generate more RPM at full throttle on every prop, and also consume more current at every RPM. And this is because when you have a motor with the same kV, the relationship between the torque that the motor produces and the current that it consumes is the same. So if the kV is the same, but the 2506 is producing more torque because it's a bigger motor, then it's also going to be consuming more current. There's no free lunch, I'm afraid. But now let's compare that bigger motor to a 2207 with more kV, higher kV. Now a higher kV motor is going to produce a little bit less torque at low RPMs because of joule losses. And if you want to learn more about joule losses and pretty much everything to do with how FPV motors work, I've got a Motor 101 video, which I'll link down in the video description. A motor with a higher kV is going to have a higher no-load RPM, i.e. a higher RPM where it generates zero torque. And you can see that it's able to produce more RPM and therefore more thrust on that 50-30 prop than the larger 2506 motor. And it's actually able to produce the same thrust on the 50-45, but then you can see it starts falling behind the 2506 on the heavier props, something like a 50-51 or a 60-40. So we can see that a lighter prop is going to perform better with a higher kV motor of a slightly smaller size, whereas a much larger prop is going to be performing much better with a larger motor with a lower kV. A bigger motor is going to stay cooler because it's got more surface area to cool down, and it's going to have a lower current density, so you're going to have less resistive heating. The bigger motor is going to provide more thrust, but it's going to draw more current to do it. You can't get around that. The cons of a bigger motor is it's heavier and actually probably less responsive, particularly if you're using it with a very light prop, because it's actually the motor's mass that it needs to accelerate more than the prop's mass. Higher kV motors provide more thrust and more power for the same weight, so you're getting that extra performance for free in terms of weight. And they perform much better on lighter props, which is what most people are flying nowadays. The cons of a high kV motor is that they're drawing more current, they're producing more power, they're consuming more power, but they're still a small motor with a limited surface area. So they do tend to get hotter. And particularly if you're spending a long time at very high throttle, then they are more likely to overheat. One of the results from my testing that I wanted to call out really clearly is that I found that 25mm or 2506 sized motors offer really no benefit over a 2207 size motor for even a relatively steeply pitched 5-inch prop. If you like the extra thrust and power that the 25mm or 2506 size motor gives you, then I would suggest considering a 2207 motor with around 2000 kV on 6S to achieve equal performance on most typical 5-inch props, whilst saving you up to 30 grams in weight. And 30 grams, particularly when it's 30 grams on the ends of the arms, is a lot in terms of the moment of inertia of the quad. And it should really significantly improve the flight performance. In my opinion, the 25mm or 2506 size motor is better suited to something like a 5.5 or maybe a 6-inch prop, where that prop has more moment of inertia, and therefore the extra torque that the larger motor can provide is going to be better utilized. If you're looking to try and figure out what size motor is appropriate for a tri-blade prop of a certain diameter, then I think this chart could be useful for you. I've listed out a lot of the typical motor sizes, and listed them out with the sort of prop diameters that they're typically run on and that people have good experiences with. So if we look at 5-inch props, you can see that we have 2207, 2306, 2107, and even a 2205, which is a more traditional motor size for 5-inch that we used to fly a long time ago. If you look at these larger motors, the 2506 and the 2208 size motors, you can see that they're significantly bigger than these, and they sit better in the sort of 5.5 or maybe even 6-inch category. And obviously there is some wiggle room here. If you're running a very light prop and you're looking to save motor weight, you can err on the lower side. If you're running a very steeply pitched prop, or you're running a prop with more blades, or you're running a bullnose prop, then you can err on the higher side. But this dotted line here should be good for a typical tri-blade prop of a given diameter. So that brings us to conclusions. And I'm going to take you through all of the motors that I've tested and give you my opinion on each of them. And hopefully by the end, you'll have enough information to decide which motor is right for you. I've divided the motors into 3 categories to make things a little easier to compare them. I've got motors that are 5-inch size with moderate kV, 5-inch size with higher kV, and then larger motors that are more suitable for 5.5 or 6-inch props. So let's get into it. We're going to start with 5-inch motors with a moderate kV and the Emax ECOII. Now, this is a great budget motor. It's very inexpensive. It's pretty efficient. It produces plenty of thrust and power. It does have a 2-piece bell, so there is that durability concern that the bell might separate in a hard crash. But it's a relatively inexpensive motor. If that were to happen to you, you'd probably be happy to go and buy another one. And it's a great benchmark motor to compare other more expensive motors against, because it just does so many things so well for such a low cost. Obviously, with such a cheap motor, the quality of the bearings is perhaps not going to be so high. And maybe you would expect the durability of the bell also maybe not to be quite so high. But I fly these and I find them fine. Let's look now at the RCinPower Smoox 2306 Plus. Now, this was a pretty efficient motor. Not the most responsive, not the most powerful or thrusty, but the slightly shorter stator and slightly wider stator is going to improve cooling. So this is going to be a good motor if you're looking to run high in the throttle a lot of the time, perhaps because you're carrying a heavier payload like a camera or something like that that's quite heavy. Let's look now at the WASP Major 22.6 by 6.5, 1860 kV, strange size. But again, it's really well made, nice neat windings, very tight air gap. RCinPower clearly have the tolerances on their manufacturing sorted, because it's really impressive how tight they can make these air gaps. And it's a very efficient motor again. So similar to the Smoox, it's a nice efficient motor. A bit of a bigger motor, so it does produce a little bit more thrust, and it's a little bit more responsive, which is good to see. And I like the color scheme, yellow and grey. There's not much more to say about this motor other than to recommend it as a pretty fine choice. The final motor in this category is the iFlight Xing 2 2207 1855 kV. And it's a Unibell design again, so not going to have any problems with dropped bells. And it's also got that little O-ring that iFlight include in their motors to protect the bearing, which should give it a little bit of an edge in terms of durability in that axial crash situation, which could damage the bearings on the other motors. This motor has just a little bit more protection. It's a nice neat winding. The air gap isn't quite as tight as what's achieved by RCinPower, but it's very close. It also has these slotted magnets, which give it a faster responsiveness in terms of acceleration, at the cost of slightly slower deceleration, I think. Overall, it's a really, really well-made motor, and it's one of my favorite motors. It's not the most thrusty, it's not the most powerful, and that actually means that you do get more low throttle resolution because the motor's just producing a little bit less thrust, so you get a little bit more resolution. And of course, I like to improve that by using a little bit of throttle expo as well, and sometimes even a throttle scale, just to make it even more sensitive in terms of throttle. Certainly, I would say takes the prize for most technologically advanced motor in this category with the addition of that little O-ring. Now we come on to the high kV category, and we're going to start with the WASP Major 2020 kV. Now, this motor put up the same thrust numbers, the same performance as the larger 25mm size motors. So it's a really powerful motor. If you're looking for that top end thrust and performance, but you don't want the weight of a 25 or 2506 size motor, then this could be a great choice. Very tight air gap again, very neat windings. RCinPower know what they're doing, and a nice color scheme as well. So there's a lot to recommend this motor, particularly if you're looking for that top end thrust and power. And I would say on a 5-inch prop, I would recommend this over any of the bigger motors. The next motor to talk about is the Xing 2 again, but this time 1950 kV. So we've increased the kV, and that puts this motor into the high kV category. And all the same things apply: Unibell design, O-ring, nice neat windings, slotted magnets to improve responsiveness. All of that's absolutely fine. This doesn't produce the most thrust in this category. That was the WASP, but it does produce a lot of thrust. So you're really getting up there close to what you can get with a larger 25 size motor. And because it's a little bit of a more moderate kV, 1950 rather than 2020, it is going to be a little bit less prone to overheating, which I think is important to consider with these motors, because the high kV category is prone to overheating in general. The GTSV3 2107 from RCinPower, 1980 kV. It's competing with the WASP 2020 kV for most insane motor in my test. Again, this thing put up thrust numbers very, very similar to what we saw with some of the 25mm 2506 size motors. It got really hot doing it, to be fair. So you wouldn't want to be at high throttle a lot of the time with this motor. It's going to get really hot, particularly if you have a relatively high-pitched prop. But if you've got a lighter quad and you're looking for, really punchy performance, or you're running a light quad that's going to deload as it accelerates. So that's an important feature. As the prop accelerates through the air, it's going to unload, and that's going to reduce the demand of torque on the motor. Then this could be a really, really great choice. A lightweight racing quad, I think, could really benefit from the performance that this provides. And also, if it's a light quad, it's probably not going to put the motor under so much load, and you're not going to have it getting too hot. So definitely a racing motor or a lightweight 5-inch motor. Not really suitable for a heavier 5-inch quad that's going to be carrying a GoPro or anything like that. If you're looking for something to do that, you should probably look in kind of the more moderate kV category. Now we come on to the big honking motors category. These are motors that really are just too big for 5-inch props, in my opinion, and they're much better suited to 5.5 or maybe 6-inch props. Starting with the iFlight Xing 2208 1800 kV motor. This was the most efficient motor in my testing. It didn't produce the most thrust of these larger motors, but it is very, very efficient and also very responsive, more responsive than either of the 25 sized motors. So that's worth bearing in mind when you're spinning a larger prop and you're wanting to carry a GoPro and you need that platform to be very, very stable. Responsiveness is key, and the 2208 really delivers that because of its taller, narrower stator. If you're running it at a very high throttle all of the time, I would worry a little bit about it overheating, but it should be absolutely fine for typical freestyle flying. It's only if you were running a very, very heavily laden Cinewhoop, something like that, where you would have to worry. Normal 5.5-inch quad or 6-inch quad is going to be fine. I would probably target this at 5.5-inch more than 6-inch, only because this is the motor that I fly on my 5.5-inch quads. So I have a lot of experience with it, and I know it performs very, very well. So now it's time for the FPVCycle Imperial 25mm. So things I like about this motor: it's nice neat windings, reasonable air gap, reasonably tight air gap. The color scheme is really, really nice. I love the look of the motor, very minimalist. The white wires are awesome. Things that I'm less keen on: it's not really a 5-inch motor, this. It's much better paired with a 5.5 or even a 6-inch prop. It's a little bit too big and heavy to be truly responsive on a 5-inch prop when you're comparing it up against 2207, 2107 motors. So, or a 2208, which is more equivalent in terms of volume. It's less responsive than those. In terms of thrust and power, it does produce a lot of thrust and a lot of power. The comparison should really be to the higher kV motors in the smaller sizes. So it's going up against the high kV motor category, and it consumes about the same power and produces about the same thrust as those. In terms of weight, it's nearly 40 grams, so it's a little bit on the heavy side for a 5-inch motor. I'd prefer to see it down sort of around 33, 34 grams. This is really better paired with a 5.5 or a 6-inch prop. That's how you're going to get the most out of it. That's where it's going to perform best. And also not a situation where you're going to expose it to too many heavy crashes so that you don't get the dropped bell issue. So that's where you're going to get the most out of this motor and where you're going to enjoy it the most, which is the most important thing, right? And the final motor we're going to look at is the iFlight Xing 2 2506. So this is the same size as the FPVCycle Imperial 25mm. It's the same kV, it weighs pretty much the same. It produces a little bit more thrust. Marginally, it's a little bit less efficient, marginally, but it's got a Unibell design and an O-ring. So if you're looking for a really durable 25mm motor that's not going to have issues with dropped bells and a little bit more durable in crashes, then this might be for you. It's going to have almost identical performance to the FPVCycle motor in terms of, low throttle control. I go on record as saying these big motors have worse low throttle control than smaller motors, but it's going to have the same low throttle control as the FPVCycle motor, and so it could be a good choice. I don't know if it's a little cheaper as well. The FPVCycle is pretty pricey. I hope that you enjoyed this video and that you now feel like you've got the information you need to decide which 5-inch motor is right for you. If you like this video, please go down and hit the like button. That helps other people see it. And if you want to see more videos like this, make sure you're subscribed, because I do quite a lot of different motor testing and I've got some more planned in the future, featuring more FPVCycle motors as well. If you enjoy this channel and you want to support me, then the best way you can do that is through Patreon. If you feel like I've earned your support, you can join from just a few dollars a month, and that gives you access to special areas of my Discord server, sneak peeks of the projects that I'm working on, and also more opportunity to interact with me and hear about all the kind of testing that I'm doing and interesting stuff that I'm finding out. If you don't feel like I've earned it yet, please keep watching videos until you do. But if today's the day, I'd really appreciate your support. That's all I have for you for this video. So until next time, I wish you all very, very happy flying.